It's setting up.
Mm-hmm.
Okay, we are now on YouTube. So let me start with a brief introduction of today's seminar. So today we are very happy to have Professor Ding Pan from Zhejiang University to give a CFS seminar. So Dr. Pan is currently an associate professor of engineering mechanics at Zhejiang University, China. So he received his PhD in fluid mechanics from Zhejiang University in 2011. And then he was a postdoc research fellow in National University of Singapore from 2011 to 2014. And Dr. Pan's research interests focus on modeling of suspension at mesoscale. So Pan and Dr. Pan, please start your seminar.
Okay, thank you, Zhen, for your invitation, and also we're glad to be here to join this complex phase and soft matter seminar. And I think I should say good morning and maybe good afternoon and good evening, everyone. Thanks for all of you joining my talk. Okay, actually, I am a little upset for this talk since this is my first English presentation since 2019. And also, what I will going to present is quite very preliminary results from our group very recently. So maybe something, some results is not new, which has been published by some others in the literature, and some is ours. Okay. Today, my name is Pan Ding. I'm from Zhejiang University and Hangzhou, China. And today my talk is about rheological investigation of suspensions with mesoscopic modeling. And in this talk, most of the simulation is done by my graduate students, Wang Jinghe. So I just thank to him. Okay, my talk has 4 parts. First is the background. I will try to explain what is suspension and what's the interest for the study of suspension, and then come to 2 major parts of my talk. One is about the suspension of spherical particles. Actually, the spherical particle suspension has been studied quite well in the community, and especially in last 10 or 20 years. And many of the work focus on the shear viscosity and its relation to the microstructure in the suspension, and also the aim of the study is trying to construct or build up a constitutive model or constitutive equation for suspension. So they come to first go to the very typical and also simple case for the suspension of spherical particle. And my second part is about the suspension of 2-dimensional sheets, or you may also call it the platelet particle. And in this part, it is different from the first part. First, it is focus on a different flow condition. We focus on elongational flow, be different from the shear flow. And then in elongational flow, we try to measure the elongation viscosity and also try to connect it to the normal stress difference of the suspension. And this is the 2 major parts. And in the end, I will give a conclusion. So first, let's go to the first part about the suspension of spherical particles and some backgrounds. First, we need to give a definition of suspension. Suspension is defined as a heterogeneous mixture in which the particles are spread throughout the liquid without dissolving it. And actually, in general, the particle could be the rigid or solid particle, or even be droplet or bubbles. And here I just give some example of suspension in nature or in industry. Like in nature, we have we encounter some mud slides or mud avalanche, then it will be a disaster. So we need to understand what mud is and what's the property it is. And in industry, some typical example is, for example, energy. You have crude oil, and you may have some wax particle or some oil droplet inside, and hydrate, you may have some bubble or some gas. And some advanced material like propellant for the rocket, then sometimes you need to the propellant from solid state to liquid state, then you need to the material to be shear thinning. And also the foam metal, you want to be the metal to be lightweighted, then people want to try to pump some bubbles into the liquid state metal, then make it made up to the foam metal. So all this example is about suspension. So we need to understand what's the property, especially its rheological properties of suspension. And the study of suspension was come back to the early year in 20th century. The first famous work is about Einstein. At that time, they considered they focused on the viscosity of the suspension, and they also always treat the viscosity of suspension as a function of volume fraction of the solid part. So Einstein, as I know, when he did his PhD thesis, and he was trying to deduce the dimension of some kind of large molecule, and from the viscosity of the solution. So he come up with this formula to predict the solution viscosity. And while this equation is only available for a very dilute situation, which I just put the curve here, the dashed line here. But at least it gives a first theoretical prediction of the suspension viscosity as a function of volume fraction. And in 1970s, Batcher and Green, they come up with another equation based on the Einstein's equation. They put a third term here by considering the hydrodynamics between particles, but it is still far away from the experimental data. Like if we put the formula here, it will be like here. So, and in 1990s, John Brady from Caltech, he gave another prediction of the viscosity, and it will be quite a match to the experimental data very well. And while in this equation, you have another parameter, the phi max. It is normally about the represent the random close packing of the system. So it normally choose equal to 0.63 or 64. And in this state, the suspension become kind of jamming. So the particle inside of the suspension will not move, become kind of a solid state. So this is phi max. While all these equations is just the shear viscosity of suspension as a function of volume fraction. So this is, we also normally call it is a rate independent suspension, which means the shear rate or the shear stress or the velocity you apply to the fluid is quite low or close to zero. And in this situation, the Reynolds number or the Stokes number of the system is close to zero. So it's quite a limit. Actually, if you consider a finite shear rate or finite shear stress, the situation becomes different. So this is the situation for when you apply a finite shear rate. So the suspension will be either shear thinning or shear thickening. Here is the experiment data from the review paper by Wagner and Brady in 2009, and it is experimental data for the viscosity of colloidal latex dispersion. And then you can see when the volume fraction of the latex come up to like 40%, then the viscosity will first decrease with the shear stress and then increase. So it exhibits like shear thinning first and then shear thickening. While shear thickening, I think the phenomenon is quite familiar to everyone. Like you will see when the fluid or the suspension tend to be shear thickening, then you can work on it and you will not immerse inside of the fluid. Well, another property is shear thinning. When we talk about the shear thinning, it's normally about the polymer solution. Like you have some polymer inside the mixture, then it will shear thinning. Like this example show, when you press quite a large pressure in the tube, then the polymer solution will come out. But when you apply the gravity is not high enough, then it will not move. This is shear thinning. Well, for suspension, it also shows shear thinning. This is also an example experiment data from Rheological in 2000 years, and he put some gas particles inside of the gasoline and also water, and measure the viscosity of the system. It show us the shear thinning. The viscosity come down, and with the increase of the shear rate. So this is the two major rheological property of suspension, which is shear thinning and shear thickening. And actually, in recent years, the shear thickening has been studied quite well. Here is mostly we can refer to a review paper published in 2020 on the annual review of fluid mechanics by Jeff Morris. For shear thickening, there are the two major parts or two major groups. First is the continuous shear thickening, which means that if the volume fraction of the suspension is not very high, like around the 50%, then the viscosity will increase gradually with the shear rate. And in this part, when the system tends to be continuous shear thickening, it is majorly caused by the particle-particle interaction along the complex axis. So you can see here this kind of load is represents the particle-particle interaction. Another group of shear thickening is called discontinuous shear thickening, which means when the volume fraction of the particle come up to like 55%, then the viscosity will come up rapidly or discontinuously to a very high level, and the system tends to be a discontinuous shear thickening. And in this situation, the particle interaction become quite isotropic, or you can see the particle interaction becomes like a net, the force chain net, kind of this. So which means the particle interaction becomes stronger. And here is another simulation results. It shows us that when the system turns up to be shear thickening, and the contact force between particles dominates. So this is a first understanding of first results showing that what's happening when the system comes to shear thickening. Another part is shear thinning. The study of shear thinning of suspension may be a little bit earlier than the shear thickening, but at that time, most of the study focused on the colloidal suspension. The colloidal suspension means that the solid particle inside the suspension is a little small, which means the size is less than normally 1 micron. And in this situation, the Brownian motion of the particle should be considered. So in this case, then the Brownian motion try to make the system to be equilibrium. But when you apply a shear stress, then the hydrodynamic interaction will dominate. Then the particle will, firstly, under the Brownian motion, the system will try to be isotropic. While if your hydrodynamic interaction turn over the system, then the particle will try to be layer by layer, so it becomes shear thinning. But besides the colloidal suspension, another major parts in the community is about non-colloidal suspension, which means the particle size is quite large. And in this situation, normally we need to the Brownian motion or the Brownian force is neglected. But in this part, as mentioned in the experiment, we also find shear thinning. But in the numerical simulation, it's hard to produce the shear thinning phenomenon. Some efforts have been put in this part, but it's still, I think it's still an open question to answer why shear thinning still happen in non-colloidal suspension. Some effort, I just name a few some efforts in this part. The first one is in 2016, a paper published in PRL. They consider that the solvent, meaning the liquid, will be shear thinning, which means when the two particles come to closer and closer, the liquid layer between the two particles will suffer quite a higher shear rate. And normally, if you have a silicone oil as the solvent fluid, and it will show constant viscosity at normal or small shear rate, but it will a little bit shear thinning at high shear rate. So they consider this situation, then they incorporate the lubrication force into for the two particles to become a shear thinning lubrication force. And with this kind of lubrication force here, and they will get a shear thinning results, but you will see that the viscosity only change a little bit. Compared with the experiment, the viscosity will change an order. So this is just, and I think it's just an attempt to try to explain what is shear thinning, but it's not, I think it's not fully answer the question. Another attempt is in 2019, a paper published in CFSM. They try to incorporate another model since they consider the looseness of the particle, and on the surface, if you have a looseness, then there will be some asperity, and they consider this kind of asperity, the contact of this kind of asperity is plastic, which means the friction coefficient is not a constant anymore. Then you need to this coefficient will be decreased when the contact comes stronger. So in this model, they also can predict the shear thinning, but as we know that contact only appeared at a higher shear rate, while from the experiments, we will see the shear thinning at a low shear rate. So I think it is the shear thinning of non-colloidal suspension is still an open question. Another interesting work I should mention here is about some experimental considering the microstructure of the suspension. Here is a paper published in on non-neutron fluid mechanics. They have two systems. One is the glycerin and the glass particle. Since the glycerin is a polar media, it will have a very strong interaction with the glass particle, which means on the surface of the glass particle there will be a layer of glycerin, and this kind of layer will avoid the particle-particle interaction, which means in this system you will not see some kind of particle clusters. And with this system, since you don't have any kind of particle clusters, then you will not find any kind of shear thinning properties of this kind of suspension. Another system is a mineral oil and glass particle. And since the mineral oil is non-polar, so it does not have a strong interaction with the glass particle, then you will see at a relatively low shear rate, there will be quite a lot of particle clusters inside the suspension. And as the shear rate increase, this kind of clusters will be destroyed by the flow or by the hydrodynamic interaction, and then the whole system turns to be a shear thinning. So this experiment tells us that maybe the morphology or the topology of the suspension or the particle cluster will be an important aspect to determine the system to be whether shear thinning or not. Okay, I just review some of the work, and here I come to a short summary. So as mentioned, as I mentioned in the previous work, and actually in the suspension, the particle inside the suspension will have some kind of different kind of interactions. Here, just to name a few, like repulsion force due to the electrostatic charge, and attractive force maybe come from the van der Waals interaction, and also a friction for the particle-particle contact, and also hydrodynamic force. And sometimes, if you consider small particles, you need to consider Brownian motion. So all this kind of particle interaction, we need to understand what's the effects of each of the interaction is. This is one question we need to answer. Another is here is another paper. They conclude the whole figure. They try to give a whole figure of the suspension and its viscosity with the shear rate. They mentioned that when the suspension was imposed by a small shear rate, the DLVO force will dominate, and it comes to shear thinning. And with the increase of shear rate, then come to become a Newtonian, and then shear thickening and come from the contact force, and then shear thinning again also from the reduced friction. So this is a whole figure of the suspension. But another question is, during the whole process, what's the microstructure? What's the evolution of the microstructure? So we try to correlate the microstructure and the macro or the bulk rheological properties. So this we doing our simulation, try to answer these few questions. Okay, here comes to our model. Okay, I think I need to speed up. We do a simulation with hundreds, 1,000 particles, and in this part we don't simulate the fluid. We just adding some hydrodynamic interaction between into the particles. Here is the Stokes drag and the lubrication force, and then we add some contact force on the particles. Also the LVO interaction, which includes the repulsive force and the van der Waals attractive force. And we do the simulation with in lamps. First, we do some validation. Here is a simulation comparison, a comparison with the data in the literature. It is a suspension. You impose a shear in this direction, and then you also impose oscillation in this direction, and you will capture that the viscosity will decrease as the oscillation frequency increase. This is an interesting phenomenon. But here we just do the same kind of simulation and try to validate our model. And another data is we consider a repulsive system, which means we only incorporate the repulsive force into the system. We don't bring the attractive force inside. And in this part, we can see that we can capture the shear thickening when the volume function is high. And in this part, we can also calculate the contribution from different forces. And you can see that when the system becomes shear thickening, the contact force dominates. And after that, we try to understand since in the repulsive system, what's the cause or what's the reason of shear thinning. You will see that even in the repulsive system before the shear thickening, you will have a short range of shear thinning. And in this range, which we plot all the pair distribution function of each of the particles, and you will see that as the shear rate increase, the peak will decrease, which means the effective particle size or the particle distance decrease, which means that there will be an effective particle size caused by the repulsive force, and as the shear rate increase, the hydrodynamic force dominates, then the effective particle size decrease, then cause the shear ceiling. And to confirm this, we also study the effects of repulsive force. Here we just vary the parameter, the d by length. You will see we have 3 different value of d by length, and you will see the viscosity results here. And after this point, all the system shear ceiling and the curve collapse, which means that after when the system becomes shear sinking, the contact force dominates, and before the repulsive force play the crucial role, and it results the shear ceiling of the system. And then after that, we bring the attractive force inside the system, and normally the attractive force is in this form, and here A is a parameter, the Harmach constant, and we vary A, and then you will see as the attractive force increase, the system become turn from a shear sinking curve to a purely shear ceiling curve, and this is quite interesting. And if you consider the first, here is a contact number of the system, then you will see with different attractive force, the contact number always increase. And another is the force contribution, and you will see for this kind of curve, at the first part, the real force, also the repulsive force will dominate, and after then, the contact force will dominate. While for the purely shear ceiling system, the contact force will dominate. So we try to understand why. So we need to go deeper into the microstructures. First, we plot the radial distribution function. This is for the repulsive system, and this is for attractive system. And you will see at a low shear rate for the repulsive system, the ring, which means the particle-particle interaction happens, is kind of isotropic. While as the shear rate increase, the ring will concentrate on the complex axis. This is for the repulsive system. While for the attractive system, you will see whatever the shear rate is, the ring is always concentrated on the complex axis. So this results indicating that there might be some difference in the microstructures for the repulsive system and the attractive system. So we just going deep into we consider the particle clusters. You will see this is a very low attractive force, more similar with the repulsive system. Then you will see as the shear rate increase, you will find some particle clusters will form. While for the attractive system or the purely shear ceiling system, you will see as the shear rate increase, this kind of particle clusters is destroyed. So this is too significant. This is the significant difference between the purely shear ceiling system and the shear ceiling and shear sinking system. If we do the statistic analysis of the clusters, you will see the significant difference is about the cluster size. For the purely shear ceiling system, you will see the cluster size will decrease, will getting smaller, while for the other system, the cluster size will getting larger. So the cluster size, the curve shape is more close to the viscosity curves. So this is the one finding, the first finding of our simulation. And then we also consider the cluster morphology, and we define the gyration tensor in each clusters. Then we pick up the diagonal and then define the relative shape and isotropy of the system. And you will see for the purely shear thinning system, which means the attractive force is very large. The system, the clusters is normally very close to the isotropic case, since the kappa square, when the kappa square equal to 0, it is a spherical shape. And while for the repulsive system or the weak attractive system, the cluster morphology will be quite anisotropic. Okay, this is the first part of our simulation. Then let's come to our second part about the suspension of two-dimensional sheets. And in this part, as I mentioned before, we concentrate on the elongational flow, and this is an example of our simulation. First, I need to see a little bit about the elongation flow, and actually, in the study of suspension or even in the non-Newtonian fluids, most case is focused on the shear flow. But if we want to create a general constitutive modeling, we need to consider different kind of flow conditions, and the elongation flow is another typical flow you need to consider. So we normally with the shear flow results and with the elongation flows, we can come up with a genetic model or genetic constitutive equation for suspension under different flow conditions. This is the same theory framework for creating a constitutive equation of the suspension. And another on the other hand is elongation flow is also have some quite familiar application in industry, like 3D printing and spinning. Example, you do the spinning for the carbon fiber, like something like that. And in our study, we focus on the platelet suspension. Actually, in fact, it's come from some graphene oxide sheet, and we try to study the geo sheet in elongation flow and what the rheological property of the whole system. While either for 3D printing or the spinning, it is kind of we also call it a filament thinning, which means you have some kind of fluids and you stretch it, and it becomes a filament, and the thinning. In this process, we can create, according to the theoretical work of Szabo in 1997, he created a force balance of this liquid, and under the definition of the elongation viscosity, here this is the elongation viscosity, then the force balance can be simplified to this one. And if we can further simplify this equation, if we consider the system to be equilibrium, then this part equal to 0, then you will see here the R mid means the radial at the middle part. So you will see the R mid is only connected to the normal stress difference. This is the first normal stress difference. ZZ means this direction, the mainstream direction, and RR means the radial direction. And the sigma here is the surface tension. So with this relationship, it means that if you want to extend the liquid as long as possible, then you need to manipulate your first normal stress differences. If you need to try to increase the first normal stress differences of the fluid, then you can extend this fluid as long as possible. And with this frame, and you also can also incorporate different kind of fluids, then you can come up with the evolution of the radius in different scaling laws. And another thing I should mention is about the elongation flow. And we can simulate this kind of filament thinning process, but it is not a steady case. So it's harder. It is difficult for us to do the statistical analysis of the stress, and also to measure the radius. And alternatively, we choose to another kind of elongation flow. This is kind of a planetary extension, and in this situation, we can do some statistical analysis of the system. So we can obtain the stress and the normal stress and something like that. And so we turn the simulation from the filament thinning to the planetary extension flow. And another thing is, since we consider the sheet, the platelet particles, so we needed to create a model, a simulation model of the platelet particle. And in this case, we have some triangle mesh to create the platelet particles, and in each element you have some interaction, like the angle interaction, the bond interaction, and also another angle interaction. With this kind of interactions, then we can come up with a platelet particle model. And if you tune the parameters, then you can come up with this kind of wavering morphology, which is quite similar to the GO, the graphene oxide. And we also do some typical case of the platelet suspension in shear flow. Then you can see the sheet will align along the shear-rated direction, and here is we measure the shear stress. Then you will see as the shear-induced alignment happen, then the shear stress will reduce. This is just a typical test. And after that, we do we consider the normal stress differences of this system. And here we may consider the first normal stress difference, which is the SXX minus XYY. Here XX is along the major flow direction, and the results give us that if here the x-axis is we call the viscous number, which is the eta S here is the viscosity of the solvent, and the gamma dot is the elongation rate, and the P is the pressure of the system. And you will see as the solvent viscosity increase, also the viscosity number increase, the normal stress difference will increase accordingly. And this results give us a approach that if we want to have if we want to extend the suspension as long as possible, then you can just increase the solvent viscosity. Like firstly you use a lower viscosity water, then you just turn the water to the gasoline with a higher viscosity, then the whole system can be extended, the suspension can be extended longer. And according to these results, we also do some experimental work. This is a cooperation with some guy in the polymer science department. You will see if we change the solvent viscosity, increase the solvent viscosity, then the elongation rate will increase accordingly. So this gives us an approach to do some industrial processing. Okay, I think talk is almost finished, then I come up with my future work, conclusion and the future work. I think I most focus on the future work. First of all, the spherical particle suspension. I think we also it has been studied quite well in the community, and I think there will be still some question. First is the normal stress difference. What's the normal stress difference of the spherical particle suspension and their correlation to the microstructures? Another is the final goal, I think, is how to close, how to make a closure of the constitutive equation. This is for the spherical particle suspension. While for the platelet particle suspension, first is since here we only consider quite the sheet quite rigid, while actually for like graphene oxide, it is flexible. So we need to correctly prediction the plate dynamics. Right? So what's the Young's modular and something like that. So we need to have a correct prediction of this. And then another thing we need to care about is we need to have a precise particle-particle interaction. Since in this system, the particle-particle interaction also quite important, which is the key for the bulk property of the platelet particle suspension. Okay, I think I just finished it here, and thank you. And any question, you're welcome.
Thanks, Dingyi. Very interesting talk. Covered the two very interesting topic, and it's quite different. It's although it's a suspension system, but the system is quite different.
Yeah. Yes.
Yeah. So if we have any question from our audience, you can unmute yourself and ask a question to Dr. Pan directly.
I have a question, if I may.
Okay. Yeah.
I'm curious about the boundary conditions on your simulation box for the LAMPS simulation, because you had a picture and
Okay.
the boundaries seem to be moving.
Yeah.
So what boundary conditions did you use and why?
Actually, this is kind of how to say, I think you mentioned you mean this one, right? Yeah, we just apply a deformation of the system, like you mean it's
Pure shear.
Yeah, we just apply a strain of the system. You make the system deform, then calibrate the deformation and give then calculate the shear rate. We do the simulation like this, and the boundary condition here is just a periodic boundary condition in 3 directions.
Okay, so it's periodic.
Yeah.
So you use a deformed box, right?
Yeah,
Fixed deformed box. So
yes.
so generate this the deformation of the simulation box.
Yes.
Thank you so much.
Yeah, just a quick follow-up, if I may, on this part. So you induce shear along one direction, but you introduce auxiliary shear in another direction. So you have 2 shear.
Yeah, this is just reproduced from the reproduction simulation from this paper.
Mm.
But while in our simulation, we don't impose the oscillation in this direction.
Oh.
Okay, we just do some validation with our simulation first.
Yeah, I think there's a question from comment. Maybe you can answer that first, and I have a follow-up question on that.
Okay.
Yeah, we have a question from Joanne. Her question is first, for the first part, is the size of cluster controllable? So you mentioned that there's a particle cluster, right?
Yeah.
And the question is the size of the cluster controllable?
Mm-hmm. Okay, I will first answer this question. I don't mean what's controllable. since the cluster size is a result of the particle-particle interaction. So we just it's like a post-processing. So it's a result. Then if you want to control the cluster size, then you can just vary the particle-particle interaction. I think it's a forward and backward process.
So there's no explicit relationship between the particle-particle interaction and the cluster size, right?
Yeah.
If you know clearly the relationship, maybe you can generate a strategy to control the cluster size. But as long as you don't have the relationship, or it's not a simple relationship, it's not that straightforward to control the size, right?
Yes.
Okay. So the second question is for the GO plate. What is the size in your simulation?
Okay. Yeah. This is a good question, and I didn't go very detailed about the simulation. Actually, we're doing this simulation with DPD. So this is a kind of DPD particles, and also you have the solvent DPD particles. So so it's harder to see what's the size of the geoplate, the sheet. And we just here I forgot to mention is we do two different scaling. When the L here is the length of the geo sheet, the delta here is the distance between each two sheet. So you will see that when the L over delta become larger, then the normal stress difference become larger, which means that if the sheet going larger, then the sheet interaction becomes stronger. Then you will come up with a larger normal stress difference.
Okay, so currently you are only work on the reduced DPD units, and you have not mapping to the physical units, right?
Yes, and okay, I can mention that in the experiments we can the sheet is around the length here is around 1 micron.
1 micron, okay.
Yeah, so a follow-up question on this graphene sheet, or those 2D sheet in the system.
Yeah.
I guess the dynamics of this will not only depend on the interaction between the 2D sheets and the particles. They also depends on the mechanical property of sheet, like the bending, stiffness, and the modulus of it. Yeah. Have you tested those, or do you?
Not yet. This is our future work. We try to do like the bending, the extension, and also the fracture.
I think we have a model that we conserve the hexagonal symmetry instead of this triangular symmetry of graphene. That way, we show that by adopting the hexagonal symmetry, we can capture some unique property of graphene. I think maybe just adopting a hexagonal symmetry may have some advantage over this triangular symmetry.
Okay.
And that can capture like bending stiffness and anisotropic behaviors better. Just maybe a general comment.
Okay, thank you for the
So I have two questions. The first one is about the cluster. So you mentioned that this is the simulation results. So how do you define what particle? Some particles belong to one cluster. How do you define this?
Yeah, this is also a good question, and it is a little bit tricky to define particle clusters. So we first we define we calculate the distance between each particle pairs. And we vary the criterion, which means the distance less than some critical value, then we consider it the cluster. So where we vary this criterion, and after that we come up that we define the cluster when two particle contact. Then we think we define it as a cluster. And then each cluster minimally it has 3 particles. Otherwise, it meaningless, I think.
Okay, this is highly depend on how you define the contact distance, right?
Yeah.
Okay. So the second question is about the graphene oxide sheet. So when you do the simulation, you mentioned that this is the normal stress difference is depend on the solvent viscosity.
Yeah.
So here, because now the sheet is kind of deformable, so you only have a single layer. So how do you consider the flow condition on the surface? Do you implement any no snip boundary condition, or you consider there is a partial snip or this kind of thing?
Yeah. Here I didn't mention that. Here we are not imposing. We just fulfill that the boundary is no slip by tuning the parameter, the interaction parameter between graphene particle and solvent particle.
Okay, but in equilibrium states, definitely you can generate this parameter control the no snip boundary condition. But as long as the surface is fluctuation and the deformation of the sheet is coupled with the local hydrodynamic flow, you may not have exact no snip boundary condition there, right?
Yes. Right. We didn't check this. So this is just preliminary results. We needed to go deep to make sure everything is right.
Yeah, I think this system have very rich physics. It's not clear that, for example, if you consider the deformation of or the fluctuation of the sheet, this where the deformation will change the friction between the sheets nearby, right?
Yeah.
So how this friction, the change on friction will affect the rheology behavior of this material is also very interesting thing. Because you can control the for example the temperature of the system. This will generate a different fluctuation pattern, fluctuation of the surface, and also the bending stiffness is also important to control the level of fluctuation motion.
Yeah.
So all this kind of thing actually will eventually will affect how the sheet interaction, right?
Yes.
Yeah.
There are indeed quite a lot of open questions in this field, and a lot of work can be done.
Okay, maybe we can discuss more in the future. This is very interesting system.
Yes. Sure.
So any other question from our audience? Okay, if not, we will end here today. We thanks again, Dr. Pan, for the interesting seminar.
Okay, thank you. Thank you all the audience.
Bye-bye.
Okay, bye-bye.